All right, so these are our notes over units of radiation. So we're going to talk about a few different things, a couple different kinds of calculations you're going to need to be able to do, and ultimately we're going to talk about how dangerous that radiation is in reality, right? So those calculations let us know how much energy is being absorbed and whether or not that might be harmful. So our first unit for radiation is actually that Curie. It's named after Madame Curie, obviously. So I'm not sure if you necessarily know who that is, but she won a Nobel Prize in physics and chemistry, I believe. So she's not only one of the first women to ever win a Nobel Prize, but also winning two in different fields makes her unique regardless of who you put her up against, right? So she's actually very, very famous for a lot of those things. She did discover a lot of things that had to do with radiation, obviously, and she actually died because of that research that she did. So, working around that radiation before she could really know exactly how dangerous it was obviously pretty harmful. She did die of cancer, and so did her husband. But these Curies, the actual unit itself, is not actually that useful for us. It's that disintegration per second. It's actually more or less that those clicks that we're getting out of the Geiger counter. Yeah, it does tell you that radiation is present, but it doesn't necessarily tell you how dangerous it is. So we're actually going to use the other units instead. Um, as these notes say, that radiation is a health risk because the energy can destroy and alter proteins. It can damage that genetic material. So being exposed to radiation is something that we are worried about to a certain extent. But again, I'm not trying to freak you out with teaching you this stuff. A lot of these things that we're talking about are actually useful for us, right? We can use radiation for a purpose if we need to. So your actual exposure to this is minimal. You don't have to worry about it in your day-to-day life, but it is useful in different contexts, so we can use it to our advantage. So the unit that we're actually going to use down there is that RAD, the radiation absorbed dose, right? So we just call it a RAD, that RAD. And that radiation absorbed dose is the amount of energy associated with radiation. And that RAD is going to be equivalent to, and we're going to use this conversion factor, 1 times 10 to the negative second joules per kilogram of tissue. So again, our energy unit in there is that joule, and then you have the kilograms of tissue, right? That in and of itself is something that you're going to have to know how to calculate what to do with, right? So if I gave you an amount of energy in joules and I told you how many kilograms of tissue we're dealing with, right, you can do a calculation right there to get a radiation unit. So we're actually going to have joules per kilogram, we're going to have rads, and we're going to convert back and forth. 1 rad is actually that 1 times 10 to the negative second joules per kilogram. If you don't want to use that in that scientific notation, just take it out of scientific notation, right? That's equivalent to 0.01, right? So when I'm going back and forth from rads to joules per kilogram, all I'm really going to be doing is moving the decimal, just kind of like a metric conversion, right? So you just have to know which way to move the decimal when it's all said and done. Otherwise, the conversion is fairly simple. So again, there's two different things that can happen here. I can have, right, an energy value, maybe it's like 95 joules. Excuse me, this pen got me there. Hold on a second. I have 95 joules and then tell you that that's going to be absorbed by some organism that has a mass of maybe 25 kilograms, and you can turn that into a radiation unit, right? So in order to get joules per kilogram, I'd have to take that 95 joules and divide it by kilograms, and I can get started here with something that can be associated with that radiation. So let me grab a calculator real quick, because I don't know what that is off the top of my head either. 95 divided by 25 is 3.8. So I'm going to have 3.8 joules per kilogram as my initial value here, right? But maybe I want that in rads. So again, I have that conversion factor from the last slide. 1 rad is that 0.01 or 1 times 10 to the negative second joules per kilogram of tissue. So if I want to convert this, 1 rad is 0.01 joules per kilogram. I can get rid of this unit, get that new unit. If I'm dividing by a 0.01, right, that's actually the same thing as multiplying by 100. So when it's all said and done, I'm going to move the decimal. This is just going to turn into 380 rads. You're always just going to move the decimal 2 places, whether it's to the right or to the left. Just depends on what thing you had to begin with. All right, so 380 rads is the amount of radiation that I was dealing with there. Otherwise, I could work the other direction, right? Maybe I could start out with a rad value, like 220 rads, and I want to turn that into joules per kilogram. So I would, again, use that same conversion factor, but this time I'm going to multiply by 0.01. And that means I'm going to move the decimal to the left twice, so I end up with 2.2 joules per kilogram. And then maybe I'll use that unit a little bit further, because I could tell you that, right, I have a mass of 100 kilograms. So if I was exposed to 220 rads of radiation, how much energy would I actually be absorbing? And you could find that out, right? You would just take my 100 kilograms and you'd multiply that by, again, this is a compound unit. You could use it as a conversion factor. I can have 2.2 joules per kilogram here. So if I multiply, I just get that 220 again, right? That's just kind of the way it works with this situation, because I happen to have a mass of 100 kilograms, and before I divided by 100, essentially, this time I'm multiplying by 100. So I basically undid that work. So the 220 rads and the 220 joules, those are equivalent for a reason. But if it's anything besides 100 kilograms, that's not necessarily going to be true. So don't just assume that that's going to be true all the time. But those are the kinds of things that I would have you do with these units, right? You should be able to take a joule, a kilogram, come up with a radiation unit, even turn it into rads, right? So that joules per kilogram, and then turn it into rads, use a conversion, or go the other way around, right? If I gave you rads, you should be able to tell me what that is in joules per kilogram, and even extend on that to maybe give me a joule value or a kilogram value, right? So all just using those units and understanding how to convert back and forth really shouldn't be that big of a problem at the end of the day. It's actually fairly simple, but you know, there are 2 types of problems I can give you. You might need to practice those a little bit. Excuse me, I went backwards by accident. So again, I have a conversion factor there. I can go from rads to joules per kilograms and back. But even then, rads aren't all that useful in the long run either, because different types of radiation actually vary in the ability to damage tissues. So some types of radiation are worse than others. So that's why we have this other thing, the REM value, that we're going to talk about next. Right? So we have rads and we have REMs, right? And it stands for radiation equivalent for man. So it accounts for that difference in ionization capabilities of like alpha, beta, gamma type radiations. Um, the equation we're going to use here, because that's actually what it is, rem, excuse me, pen being weird, rem is going to be equal to rads, whatever they happen to be, times an RBE factor. And this RBE factor is down here. It's that relative biological effectiveness, right? And that's going to be different depending on the type of radiation that I have. So the RBE value is either going to be a 1 or it's going to be a 20, right? So if I'm talking about beta or gamma radiations, those actually aren't very harmful. They don't carry that much energy, right? Remember, they're very, very small particles, right? So they can't carry a ton of energy. But beta and gamma radiations have an RBE of 1. So for them, rads and rems are essentially the same thing. Because if I take rads times 1, it's still going to be the same value. It's just now a rem value. So if I was talking about those examples I had a second ago when I had 220 rads, if I'm talking about a beta or a gamma radiation, I would just multiply by 1 and I'd have 220 rem, right? It's not even something you actually have to do. You just need to recognize when you're multiplying by 1 and when you're not. Because if it's an alpha radiation, alpha particles actually carry a little bit more energy, a significantly larger amount of energy. So instead of taking it times 1, I'd actually take that 220 rads times 20, right? Which is actually going to make this significantly bigger. So I got 44, 0, add another 0, right? Now it's 4,400 rem instead of 220 rem. And maybe that doesn't seem like it's that much bigger, but when it's all said and done, I have these different thresholds, right, on your worksheets that you do, and anytime you need it, I just give you a table that tells you those different rem values, how those would affect you, right? But we're just going to run down that idea real quick over here. You don't have to write these down because I'm just kind of, you're going to have it later to work with. If you have less than 25 rem, there's going to be no noticeable effect. So if you're exposed to that much radiation, it doesn't matter. It's unlikely that there's any damage that's going to cause any harm, and you just don't have to worry about it. But when you get between 25 and 100, that's when you're going to have a drop in that white blood cell count. So it doesn't necessarily hurt you right away, but it does hurt your immune system, and it affects your immune system so that if you did get sick, right, it'd be hard for you to fight that off, right, because your white blood cells are a big part of your immune system. Then you got the next level up, anything between 100 and 200, that's when you're actually going to have that radiation sickness. So maybe some people are familiar with what that would be like, right? When you're exposed to a significant amount of radiation, right, you can get very sick. You can lose your hair. You can have skin that sloughs off. You'd obviously be throwing up. You'd have diarrhea, right? Not going to be a good thing, right? So radiation sickness is really uncomfortable, and people that go through chemo are very aware of that, right? So, not necessarily a good thing, but at the same time, those people that are doing that chemo, they're doing it for a reason. We're trying to kill cells, right? We're just hoping that we're targeting cancer cells as opposed to, all of your other cells that are healthy and functioning appropriately. So we're using this stuff to our advantage, hopefully, in most cases, but anywhere from 100 to 200, you're going to start getting that radiation sickness. The next boundary is actually up at 500, and once you reach 500 rems, that's actually when 50% of the people, half of the people that are exposed to that much radiation would die, right? That's basically telling you that if you're over 500, you have a coin flip on whether you're going to live or die, right? Which is not very good probabilities, right? Those are not good odds for a person. So you would want to avoid that, obviously, But like we were talking about over here, there's a pretty big difference then between 220 rem where you might be sick, right? And this 4,400, which is significantly bigger than 500, right? You're probably going to die if you were exposed to that much radiation. So you can tell right away the difference between those beta and gamma radiations and that alpha radiation, right? Alpha is significantly more damaging than those other two. But that being said, alpha is the easiest one to protect yourself from because it's such a large particle, right? All you have to do is wear a paper mask and that alpha radiation can't get into your system. You would have to inhale it, ingest it some way, somehow before it could actually hurt you, right? That alpha particle is so large that it can't even penetrate your skin. So, but beta and gamma radiations, on the other hand, can actually go right through your body, right? So it's kind of hard to protect yourself from those. So there are differing levels of ionization capabilities again. So some radiation forms are more dangerous than others. But that being said, the ones that are most dangerous are the easiest ones to protect yourself from. So it's kind of it depends on the situation. Those beta and gamma radiations can still be harmful, right? It's just less likely, right, with that ×1 that you're going to reach that LD50 value, right? That you're going to end up dying because of it. So we're going to do conversions. Again, all you have to do is multiply by 1 or multiply by 20, right? And that does make a significant difference. Alpha is much more damaging than beta and gamma. So actually you had this RBE that I could have done that last slide under. So again, not really a big deal. I just kind of didn't realize I had extra space there. Health and safety though, just again to make sure you guys understand, your typical annual exposure with x-rays is less than 1 rem. It's 0.05, and you could get up to 25 rem and you're likely to have zero noticeable effect, right? So you don't really have to worry about x-rays. They're very, very small, but they would add up, right? So if you had hundreds of x-rays a day because you worked and that's what you do for a living, right? You're a radiologist, you're probably going to be exposed to a significant amount of radiation, and you have to be careful about that. Again, they have ways to protect themselves from that. Otherwise, radiation treatment, right? Remember, we're going to take advantage of that LD50 value. We actually want to expose a lethal dose, 500 rems, to those tumors to kill them, right? Because they're obviously not doing what they need to be doing, right? But you're going to focus it on that tumor, and hopefully the surrounding tissue is not going to be that affected by it. But that being said, it's unavoidable, right? Depending on the type of radiation treatment that you have, right, they can actually focus radiation on like a tumor directly and kill it. Or you can be doing chemotherapy where you're actually, that radiation treatment is going throughout your whole system, and it's actually those cells that are replicating quicker than other cells that are affected the most, which is why your hair falls out, because skin cells and your follicles are actually things that replicate rather quickly. They need to replace themselves quickly, and so does your stomach lining, which is why you have an upset stomach and why you're going to be throwing up, right? And also having diarrhea and things like that. So again, we're trying to use this for a positive purpose, but that being said, there are those negative side effects at the same time. Protection, again, comes in the form of shielding. A lot of times you use lead, but for alpha, again, you can use a paper mask, right? Whereas the beta can penetrate up to ½ a centimeter of lead, so you need to have a shield that's thicker than that to protect you from it. Whereas the gamma radiation, because it's so small, can actually go all the way through 10 centimeters of lead. So you would have to have a much thicker shield in that case, right? So when you talk about these different types of radiation, you have to protect yourself in different ways. It isn't possible to completely avoid radiation, but again, your annual exposure to radiation in general is much less than that 25 threshold. There's little to no chance that you're going to have any problems with that, but you do want to pay attention to it. If there's a possibility that you would be exposed to some kind of radiation, you would want to protect yourself, and you'd want to know that. All right, so that's all we needed to take care of there.